Okay, so at least looks like you've brought up those homework problems, so let's take a look. All right, so again, it's good that you're putting in numbers. Let's see. Huh. Okay, I didn't write this problem correctly, but you drew the correct answer, I think, anyway, based on what I drew. Let's see. 3, 2, 1. Okay, and you said these arrows were reasonable. Good. Anything in particular that's reasonable about them?
Looks like the chain of arrows started at a negative charge and ended on a positive charge, so that was a good thing. It looked like it neutralized all of the charges there.
Good, excellent. Okay, that was the main thing I was going for. You might not have thought about this, but actually you might notice this problem actually somewhat contradicts what I told you last time. Last time I told you that when there's two formal charges in the same molecule, they won't both participate in the reaction. I said that when there's two formal charges in the same molecule, they won't both participate. But now that I look at this example, I can see actually I was somewhat mistaken about that because this is a reasonable reaction. So most of the rules in organic chemistry have some exceptions. So that rule that I gave you last time was a good rule. It's true that when there's two formal charges in the same molecule, they don't. Oftentimes, they won't both participate. But there are a few examples where you can get both charges in the same molecule to participate in the reaction, and this is one of them. So anyway, this was a reasonable reaction, and it looks like you drew, changed two charges and drew in the bonds. Okay, so I'll take a look at the next example. Let's see. Okay, so you drew in... All right, you broke the right bonds and formed the right bonds, and you changed two charges. Very good. And then you said that this was not reasonable because two charges are created. All right, so actually it turns out this particular rule this reaction is fairly reasonable. I guess you should be suspicious of forming charges. However, on these problems, I wanted to start by using the rules that we've discussed so far. So what are the rules the concrete rules that we discussed so far? Well, the main rule was that when possible, you want to put a negative charge at the beginning of the string of arrows, and when possible, you want to put a positive charge at the end of the string of arrows. That was one of the important rules. You want to put a negative charge at the beginning and a positive at the end. But in this case, nobody had a negative formal charge, and nobody had a positive formal charge. So we had no choice but to use some of the neutral atoms. And the other main rule we went over last time was don't break the octet rule. So those were the only two rules really that we've gone over so far. The other rule here was to check whether we've broken the octet rule. This problem doesn't break the octet rule. For example, the middle iodine is gaining a bond but also losing a bond. So it doesn't break the octet rule. Okay. It turns out that sometimes it's okay to form two charges, although I guess I can see how you might have to be suspicious of that. Really, that's almost inevitable, though, if nobody starts with a formal charge. If none of the atoms have started with a formal charge, if you're going to do any reaction at all, it's almost inevitable that you're going to form two charges. Okay, so that wasn't bad thinking. It's true that you should be suspicious of charges, but we can't just assume this is not reasonable because two charges are created, especially because there were no formal charges to get rid of. So perhaps you can cross off that answer in the middle where you said that it was not reasonable because the two charges were created.
Okay. It looks like that iodine that has a negative charge, that then could go where that positive is, and that would balance, I guess, neutralize the whole thing in the end.
Outstanding. That's right. That's right. So that's the next step in sophistication. It's good that you're thinking about that. That product, so one thing you could say is that does not look like the final product because there's a positive charge. So you should next be thinking what would be the next step in the reaction. And you're absolutely right. That would be a very reasonable next step for the reaction. So you were right to pay attention to those charges. They don't make it impossible for the first step to happen, but they do mean that the next step is probably going to try to get rid of some of those charges. So that was a good point. Okay, so I'll take a look at the next example. The next example was cyclic, so you didn't change any charges.
Mm-hmm.
And you said it was reasonable. Well, it doesn't break the octet. Remember, the only rules that you and I have talked about so far are don't break the octet rule, and if possible, put negative charges at the beginning and positive charges at the end of the arrows. Well, there are no negative or positive formal charges there, so you can't put them at the beginning or the end, but that reaction didn't break the octet rule. Everyone who was gaining a bond was also losing a bond. Okay, so that was right. Let's take a look at the next example. 1, 2, 3, 4, 5. You said that reaction was reasonable, and it is. There's a negative charge at the beginning of the arrows. Let's scroll down a bit so we can look at the next example. Let's see. That one's kind of complicated, for a little bit weird. Okay, I think that's a tricky one. That's a tricky one, but you took your time and you got that right, so that's good. That's a tricky example. So I'm pretty sure you've never seen that particular reaction before, but now that we've learned the rules for electron-pushing arrows, it doesn't matter whether we've seen the reaction before or not. We can always draw the product by obeying the rules for the arrows, so that's some good progress. That's a tricky question. And you said that was reasonable. Well, there is a negative charge at the beginning of the string of arrows. Yep. Then the next example is another tricky one. So let's see, 2 to 9. Okay, excellent. The next example is also tricky, but you got that right. Again, I'll bet that's a reaction you've never seen before, but you obeyed the rules for the arrows and you did it correctly. That also doesn't break any of the rules we've talked about. So those last two are tricky examples, so that's good that you got those right. Then the next one, OH. That gives us a kind of a weird-looking product with two double bonds right next to each other. We haven't really seen that much of that before. And it looks like you just found a mistake. Okay, so that's good that you caught that there. That's important. We always need to change two charges, so we need to make sure that we did that. Okay, so it looks like there was a mistake there originally, but it's good that you just caught that. And did you think those arrows were reasonable?
Yeah, they looked reasonable.
Okay, fair enough. All right, in fact, all of the examples from this question were reasonable, or at least they didn't break any of the rules we've talked about so far. All of the examples here, none of them broke any of the rules we've talked about so far. Okay, well, we spent quite a bit of time going over that skill of being able to draw the product based on the arrows, and it looks like we were pretty successful with that. There was a couple quite difficult problems in there, especially the second and next to last, but you got those correct, so that's very good. All right, so let's move on to the next problem. Assign formal charges. Water, sodium hydroxide, hydronium. So in the sodium hydroxide, you knew to put in the negative charge because you saw the sodium, and you know that would be an ionic bond. On the other hand, in the H3O+, it was already drawn for you. So obviously, we shouldn't, what's the expression? We shouldn't look a gift horse in the mouth. If the problem tells us the formal charge, then we'll accept that that's the formal charge. Then the next problem has potassium, so you put in a formal charge. Then the next problem, they didn't draw in any formal charges, and there's no metals, so we just assume that it's the way they drew it, and there are no formal charges. Remember, if they don't draw a formal charge, there usually isn't one, unless there's an ionic bond. Then the next one, no formal charge. Next one, no formal charge. Then with the sodium and the CN, there is a formal charge. So notice I tried to put some molecules that were similar but different. Notice there's a huge difference between being bonded to a hydrogen or a carbon or a sodium. If you're bonded to a hydrogen or a carbon, there's no particular reason to have a formal charge if that's not already drawn in. But if you're bonded to a sodium or potassium, you know to draw in the formal charge. You can see that for the next example as well. There's bromine with potassium, bromine with carbon, and bromine with hydrogen. Well, the only case where you draw in the formal charges is the bromine with the potassium. Good. Then there's a nitrogen example with lithium. So you drew in the formal charge there. Then there was an example where I already drew the formal charge for you, a negative charge on a carbon, so we just accept that's the formal charge. NaH, that you drew in the formal charge. Okay, good. So you drew in the formal charges on the ionic bonds. That was right. Okay, excellent. So let's look at the next problem, but that's good. Now, the important thing is that from now on, whenever you're given a problem, you have to automatically put in those formal charges. Okay, so let's look at this first example here. Okay, so let's see, are you taking a look at the first example at the top?
Uh-huh.
Okay. All right. Now, something went wrong here. So remember question 2 you did very well on. Question 2 you did very well. You put in all the formal charges, but unfortunately you forgot to apply that to this problem. Remember, from now on, we have to draw in the formal charges ourselves at the beginning of every problem. Are there any formal charges we could have drawn in on that problem?
Definitely there are. Yeah, this should be a positive, and this oxygen should be the negative, which would make more sense if this were starting the chain of reactions.
Okay, yes. So let's maybe put you need to mark that problem. That's an important problem that we missed. Okay, so that's an important issue in OCHEM. So you did good on question 2, but maybe I should have emphasized the point of question 2 is now, from now on, we have to go through that exercise at the beginning of every single problem. Every single problem for the rest of our lives in OCHEM, we have to start by writing in any formal charges in ionic bonds. Okay, and then we, remember, we only talked about 2 rules last time, but one of the rules was, if possible, put the negative charge at the beginning of the arrows. So is it possible to put a negative charge at the beginning of these arrows? Yes, because there is one. So that's the preferred reaction in this case. All right, so I think you saw that issue there. All right, so those were actually unreasonable arrows. That would be an important one to review. Let me take a look at the next example. You said that those were unreasonable, and then I think I asked you to draw more reasonable arrows. So, okay, so so on this problem, you saw what the issue was, which was similar to the previous case. You drew in the negative formal charge on the oxygen connected to the potassium, and then it's better to use that oxygen. And I only asked you to write a set of arrows that are reasonable, but you went the extra mile and you wrote 2 sets of arrows that were reasonable, so that's good. You saw that maybe the oxygen would attack carbon 1 in the same molecule, or maybe the oxygen would attack, let's see, or maybe, let's see, did you do 2 different things? Oh yeah, or maybe the oxygen would attack carbon 6 in a different molecule. Okay, so those are 2 different possibilities here, and you actually, and then you even went beyond that and actually drew the products from that. So that's good practice. Let's see, 6, 7, 8, 9, 10. Okay, good. So which one is right? Which one would actually happen in this problem? Well, so far we haven't gone over the tools to figure out which is preferred. So actually, I don't think I'm going to tell you which one is the preferred in this case. All we'll say is that so far there seem like 2 possible sets of reasonable arrows. There might even be, so far there seem like 2 possible sets of reasonable arrows, and so far we haven't gone over the tools to figure out which one is preferred. But anyway, the first set of arrows was unreasonable because it wasn't using the oxygen with a negative charge. That's most important. Okay, so let's take a look at the next example. You said that was reasonable. Okay, good. It looks like you actually did a little more work on these problems than you needed to. It looks like you were actually drawing the products as well. For these problems, it wasn't necessary to draw the products, but it's still good practice. So it was still good practice to go ahead and do that. These were reasonable. There's a positive charge at the end of the string of arrows. There's no negative charge at the beginning of the arrows, but that's okay because there are no negative formal charges in this problem. And then you went the extra mile and actually drew the product as well. Okay. Good. All right. So 4th, you said that was reasonable. Yeah. So there's a positive charge at the head of the arrows. Very good. All right. So let's scroll down. Okay. All right. Now, why did you say this was reasonable? Well, probably because there's a negative charge at the beginning of the arrows and a positive charge at the end. But do you remember there was one other important rule that you and I went over last time? The other important rule was don't break the octet rule.
Yeah.
Now, how can you tell whether something's breaking the octet rule? Do you remember, how did we decide how to tell whether something's breaking the octet rule? I'm not sure if you remembered that. There's actually, remember we saw you don't have to count lone pairs and you don't have to count bonds. It's just if something is starting with a complete octet, it can't gain a bond without losing a bond. If something is starting with a complete octet. So first of all, did the sulfur here start with a complete octet or not?
It appears so. Yeah, I'm a little hazy on when you can tell if it has a complete octet, if it has a charge on it already.
Okay, that would be a good thing for us to talk about. We actually talked about that a bit in our last session, but let's review that. What we said is that in OChem, almost everything has a complete octet, whether it has a charge or not. What we said in our last session is that almost everything has a complete octet, whether it has a charge or not. So all you really have to do is just memorize the couple of exceptions that don't have complete octets. All that's really necessary is to memorize that there's a couple of exceptions that don't have complete octets. So what we only mentioned a couple of things that don't have complete octets. Remember we said carbons with positive charges do not have complete octets. Carbons with positive charges do not have complete octets. And we also said hydrogens with positive charges do not have complete doublets.
Yeah.
And that was pretty much it.
Okay.
That was pretty much it. And we said that just about everything else, whether it has a charge or not, you can assume that it has a complete octet. Let me go back to my screen and write that out again, because that's quite important. Okay, so here's this important rule that we talked about last time. In OChem, these are just about the only things with incomplete octets or doublets. Pretty much everything else, whether it's charged or not, has a complete octet. Tell me when you have that written down.
Okay.
Okay. There was one other exception I think we talked about last time. A neutral metal or semi-metal also has an incomplete octet. And the examples that come up in OChem are aluminum, boron, which is a semi-metal, and iron.
Okay.
And again, those have incomplete octets. Also, one other exception is, this is not really very important, metals with positive charges have incomplete octets, but now I'm going to erase that. That's not worth really writing down, because remember, those are just spectators. They're not going to be participating in the reaction, so it doesn't really matter whether their octet is complete or not. All right, so basically, these are the only things with incomplete octets. You can pretty much assume everything else is neutral or charged. So notice, you don't need to try to count the lone pairs and bonds to figure out whether something has a complete octet or not. This is a much faster and more direct approach, which is important because we always have to check whether we're breaking the octet rule or not. Okay, and also let's review the rule. How do you know when you're breaking the octet rule? Well, the rule, remember, is an atom that starts with a complete octet cannot gain a bond unless it makes room by simultaneously losing a bond. Tell me when you have that written down again.
Okay.
By the way, notice it's okay to gain a lone pair. We talked last time about how that would never break the octet rule. The only time where you have to worry about breaking the octet rule is when you're gaining a bond. All right, so let me take another look at your screen. Let's see. So let's look at this example at the top of the screen here. Did the sulfur start? Let's see. Did the sulfur start with a complete octet? Yes. How do we know? Well, just because it's not a carbon or a hydrogen with a positive charge. We know that pretty much everything else starts with a complete octet. Let's see. All right, and is the sulfur gaining a bond?
Yes.
All right, so is this rule reasonable or unreasonable? Would this rule break the octet rule?
It would break the octet rule.
Yeah, so that was actually an unreasonable arrow. That arrow was actually unreasonable. Okay. All right, then the other thing we're supposed to do then is, can you think of a way to fix the arrows so they would be reasonable? Or draw new arrows so they would be reasonable?
Yeah, I think you could. You could have that negative charge go on that hydrogen to form a bond with the hydrogen between bromine and hydrogen, and then break the bond with sulfur so that you would
Great.
actually...
Okay, and we won't actually draw the product from that to save time, because I think you made good progress on that. I think you've done really good progress on learning how to draw the products based on the arrows. So we don't need to keep practicing that right now. Now we need to focus on drawing the arrows. Okay. By the way, that's very good. Now, in order for those arrows to be legal, you need to draw the bond between the sulfur and the hydrogen. So you might have to draw a tiny little bond. There you go. Good. Or oftentimes you have to erase and redraw, but here you fit that in. Okay. Now these are reasonable. Because now is the sulfur gaining a bond with these new arrows?
Yes, it is gaining... Well, oh, sorry. No, it's not gaining a new bond. It's just breaking a bond.
That's right, gaining a lone pair. That's why it doesn't break the octet rule. Yeah. Remember, you only have to worry that you might break the octet rule when you're gaining a bond. Gaining a lone pair will never break the octet rule. Okay, it's good that you marked that question. That's an important question that we actually ended up missing there. All right, so let me look at the next example. All right, now you said this was unreasonable because it was creating charges. Now that's on the right track. We've seen we should be suspicious of creating charges, but maybe that's not quite the best way to put it, because there are some reactions that do create charges. There are some reactions that do create charges. So to be more specific and use the exact rules we've talked about before, this is unreasonable because the positive charge is in the middle of the arrows. That would be a better way of putting it. Remember, we've seen when possible, we want to put the positive charge at the end of the arrows and the negative charge at the beginning. So that's the best way. Now, the reason why that's unreasonable is related to the idea that it creates charges without removing the charge. So you were on the right track. You were on the right track, but I think this is a better and simpler way to put it. Because sometimes it's okay to create charges. The point here is we're creating charges when it wasn't necessary. But a more straightforward way to see this is it's not good to have the positive charge in the middle of the arrows. Okay, so your idea was on the right track, but I think this will be a better way to think about it. All right, so those arrows were not reasonable. We should not put a positive charge in the middle of the arrows. So you tried to draw new arrows. Good. You did draw then the new arrows, and those were reasonable because now the positive charge was at the end of the chain of arrows. Okay, and then you went ahead and actually even drew the products based from that, and that was correct. Okay, good. Okay, so that one you got correct, but we put a better way to see what was wrong with that. All right, so let's look at the next example.
Okay.
Let's see. You said that those were reasonable arrows, and that's true. They are. Okay, and you also, you drew the product correctly from that, but the key thing is you saw those were reasonable arrows. Okay, good. So let's keep going. Unreasonable. Chlorine has a full octet, so it can't gain a bond. Good. That's good that you saw that. How do we know that the chlorine has a full octet? I don't know how you thought about this when you were doing the problem, but now we know it has a full octet because it's not a carbon or a hydrogen with a positive charge. Carbon and hydrogen with a positive charge are just about the only things that have incomplete octets. So we know that it has a full octet, so it can't gain a bond without losing a bond. So the first set of arrows was unreasonable. And then the new set of arrows works, because then the chlorine is not gaining a bond, but just gaining a lone pair. And then you went ahead and actually drew the product based from that. You connected 1 with 8. And then you went even further. I didn't ask you to do this, but that was good practice, and you decided to, you knew that wasn't the final product, and you tried to figure out something else that would happen. Okay, excellent. Now, what you drew there in that second step, that isn't what actually happens in real life, but it was a very reasonable arrow based on what we've talked about so far. So I would say that was good. Your second set of arrows where you have the chlorine attacking carbon 2, that isn't what actually will happen. You'll learn about the actual reaction later in the second semester, but it was a very reasonable guess. That was a very reasonable guess. So based on what we've talked about so far, that was a very reasonable guess for the next step. So that was a good application of what we've talked about. Okay, so let me take a look at the next example. Okay, now, so take a look at this example. I would say these arrows are not reasonable. What's the most direct way to see that they're not reasonable?
You're creating a primary ion, a negative charge on a primary carbon.
Okay. Now the problem is, what we've said is that you can't form primary carbocations.
Okay.
But is this a cation?
No, this is a carboanion.
That's right. So the rule that we talked about before doesn't really apply here. We haven't talked about primary, secondary, or tertiary carb anions, so we can't apply that rule here. So here's where OChem starts to get more challenging when you have many different rules, and it's important not to get them confused. Okay, so I think the best thing to do is, so let's review. We've really only gone over 2 rules so far. We've gone over 2 basic rules that I was hoping that we would practice here. I'm sorry, what were you saying?
The positive is in the middle of the chain of arrows.
That's what I was going for. Yeah. We don't want to have a positive in the middle of the arrows. What's the most important factor in organic chemistry?
The charges.
The charges. And you were trying to use the charge. But we also have to find what are the most effective ways to use it. So it turns out that one of the most effective rules is we need to put a negative charge at the beginning of the string of arrows and a positive charge at the end. We don't want to put charges in the middle of the arrows. Let me go back to my screen. It looks like for the rest of these problems, it looks like there were some of these problems in the homework we were missing. So maybe we should, as we're going through these, we should be kind of rethinking them. So one thing I think I didn't quite make clear enough is in the homework I said use the rules that we've talked about, but I didn't quite summarize enough what are the rules that we've talked about. So far we've talked about 2 rules. Here's one of the rules, don't break the octet rule. And the other rule is, if possible, put a negative formal charge at the start of the chain of arrows. And a positive formal charge at the end of the chain of arrows. So one of the implications of that is do not put charges in the middle. This rule here is very reliable. There's almost no exceptions to this. I can think of one exception. But this is pretty reliable. There's almost no exceptions to this rule. We almost never put a charge in the middle of the chain of arrows. Now, we could go further and say why. The reason why you don't put a charge in the middle of the arrows is because then you won't be getting rid of that charge. You can't get, if the charge is in the middle, it would be both gaining and losing electrons, and you can't get rid of that charge. But we can simplify things so we don't have to think through every single idea and every single problem and just memorize this as a rule. Do not put charges in the middle of the chain of arrows. Why do we want to put a negative at the beginning? So that it'll lose its negative charge. And why do we want to put a positive charge at the end? So it'll lose its positive charge. We don't want to put them in the middle because then they won't lose their charges. But we can also apply this a little bit more mechanically to save time as well. We can just memorize this as a rule. So these are the only two rules that you and I have talked about so far for evaluating whether the arrows are reasonable or not. So let's, as we go through the rest of these homework problems, let's reapply these rules. Let's think about these specific rules for each problem that we're working on. Okay, do you have these in your notes again?
Yeah.
Okay, so let's go back to your screen. Let's see. Okay. So yeah, we're looking at that bromine example. We decided that was unreasonable, and the easiest way to see it's unreasonable is that there was a positive charge in the middle of the chain of arrows. Also, you saw that when you drew the product, you had misdrawn it somewhat. You had not put in that negative charge there. Also, you actually misdrew it a little bit more because it looks like you got rid of the positive charge on the bromine. But it shouldn't lose its positive charge, should it? So maybe you can't really draw it as Br2.
Yeah.
Yeah.
So I think what would be better...
Yes, let's go ahead and try to fix the arrows.
We did that.
Great. Okay, good. And we don't need to draw the product. I think you're good at drawing the product here. So let's focus on the thing that we're having difficulty with, because I think you're good at drawing the products now. So those are better arrows, because now the negative is at the beginning and the positive is at the end of the chain of arrows. Okay. Okay, so let's rethink each of these as we go. So let's look at the next example. So think that through again. You had said originally that was unreasonable. What are your thoughts about the next example now?
Well, aluminum, the semi-metal, is an exception, right, to the octet rule.
Right.
So it seems like you, in fact, could form a bond there with aluminum and between the chlorine and the aluminum, and it would be reasonable.
Okay, yes. Now what you said originally was that you didn't say it was unreasonable because of the octet rule. You said it was unreasonable because it was creating charges. But we've seen that's probably not the best way. That's not the best way to think about these. I guess you should be a little suspicious when you're creating charges, but actually there's many times where it's inevitable that some charges are going to be created. So we can't just have a blanket rule that says don't create charges. So that's really not the best way to think about that. Maybe we should cross that out then. Instead, the point is, especially because everybody here started neutral, there's almost nothing you can do that's not going to create some charges. So remember, we've just gone over two rules. If possible, put a negative charge at the beginning and a positive charge at the end. Well, we satisfied that rule in this case just because it wasn't possible to do that, because there were no formal charges. And the only other rule we've talked about is don't break the octet rule. Well, we memorized that because aluminum is a neutral, we have a neutral metal here, it actually starts with an incomplete octet. So we know there's room for the new bond. So were these reasonable or unreasonable?
Reasonable.
All right, so we can change that as well. Okay. All right, so let's just go through and rethink our answers for each of these as we go. So rethink your answer for the next problem.
Okay. For the first rule, as far as the positive charge being at the end of the arrows, that appears fine. And for the octet rule, that also appears fine because the carbocation on carbon number 2 has an incomplete octet, so it can actually form a bond without breaking the octet rule.
That was well described. So that the way you described those, your reasoning there was exactly correct. Good. Okay, so so this one you got correct. This was reasonable arrows, and you also drew the product correctly. Okay, so that one was correct. Let's rethink our answer then for the next problem.
Okay, so well, it appears that this would be okay with the charges ending on positive, starting with the negative, but it does form a bond with oxygen, which already has a complete octet, without breaking a bond to make room for it. So it would be unreasonable unless we broke a bond to make room for the new bond.
Good. Yeah, so this is unreasonable. So for your notes, we can put in that it's unreasonable because it breaks the octet rule. Good. All right, and then we should go back and see if we can draw more reasonable arrows.
Yeah, it looks like you could do that.
Excellent. Good. Okay. Those are not necessarily the only reasonable arrows, but those are reasonable arrows. Excellent. Good. Because now you're not breaking the octet rule, because now the oxygen is gaining a lone pair, not gaining a bond. Okay. All right, so when you rethought this, originally you got this incorrect, but when you rethought it, you thought it through correctly. That's good. So let's rethink the next one. Basically, actually, I think I'm just going to have you redo this whole set afterwards, since we had some trouble with this. So you'll want to go back and redo all of these, because this is the heart of organic chemistry right here. This is where the organic chemistry, this is where we get serious. This is where things get difficult. So this will be, since we had some issues here, it'll be good to just go back and redo this set again later on your own. But in any case, let's rethink now the third example on the screen.
Okay, so the original black arrow that you had drawn appears unreasonable because it is forming a bond with oxygen, which already has a full octet.
Which you had already said before, so that's good. Yeah.
And so in order to make room for that new bond being formed, well... and
that's good that you drew in that little red bond there. Good.
Yeah, it appears that you would need to have that oxygen attacking something other than that oxygen with the positive charge, so that the chain of the arrows can end on the positive and...
Without forming a new bond.
Without forming a new bond.
Exactly. Yeah. Perfect. Excellent. Now again, that arrow that you just drew there, it's not the only possible arrows, but they are good arrows. Just to mention, another possibility would be that the water could attack the carbon connected to the oxygen rather than attacking the hydrogen connected to the oxygen. Based on what we've talked about so far, we can't really tell which is better. But anyway, the new arrows you've drawn in are reasonable. So I can see you had a good idea here. Since I had drawn that in black, you changed to a different color, so you can draw that on top of it. That was a good idea. Okay, good. So let's go ahead. All right, so it looks like actually you got that one correct originally. You saw it was breaking the octet rule. Okay, so let's rethink now the next example.
Okay, this actually looks like the same violation of the octet rule, trying to form a bond with oxygen which already has a complete bond. And so in order to do that, it's basically the same approach, that the oxygen on the right would attack a different molecule so that the chain of arrows could end on that positively charged oxygen and not create a bond.
Good. Yeah, that's right. We need to attack a different atom than the oxygen. Good. And again, the arrows you drew are not the only possible arrows, but they are reasonable arrows. Good. By the way, so notice that these last two examples on the page you had already gotten right originally, whereas the second example, originally you had gotten incorrect, even though it was the same issue, right?
Yeah.
And that second example was also breaking the octet rule, but in that case we hadn't quite seen it. And that might have been because you might not have been using the most straightforward approach for deciding whether something started with a complete octet. Now we've seen that it's actually quite straightforward to see whether something started with a complete octet, which is just to say carbons with positive charges and hydrogens with positive charges have incomplete octets or duplets, and pretty much everything else starts with a complete octet. And then we can quickly see that all three of the last examples on this page here were breaking the octet rule. But the top example was not breaking the octet rule because there you had a carbon with a positive charge. Okay, so you got that one correct originally. So let's move on then. Okay, so let's rethink our answer here.
Okay, well, the original arrow looks like it would have given that oxygen a positive 2 charge, which we shouldn't do. So, and I guess it would be violating the octet rule at the same time by having a bond broken without having it replaced by a new bond or an electron pair. And so also the chain of arrows originally did not end on the positive oxygen there.
That's right. Although those two things you said are kind of two sides of the same coin. The reason why you'd be getting the positive 2 charge is because the oxygen, the positive, was at the beginning of the arrows rather than at the end. So both things you said were correct. Both things you said were correct. To simplify things, we could just say this is wrong because the arrow is starting on the positive where it should be ending on the positive. Remember that these are rules that we're going to need to apply on every single step of every mechanism that we do for the rest of the course. So we need to streamline them so that we can use them quickly and efficiently as well. So everything you said there was right. Everything you said was right. But the most efficient way to evaluate this is simply to say the positive charge should go at the end of the arrows, not the beginning. Although you did give the right explanation for why this would give us a positive 2 charge. One thing you said that was not quite right is you said this would break the octet rule. I'm not quite sure what you were thinking, but the arrow I drew was forming a lone pair, not forming a bond. So it's certainly not going to exceed an octet. It's certainly not going to exceed an octet. It's true that it would leave the oxygen with an incomplete octet. And that's part of why this is bad. That's not really an issue that we talked about much together, though. So again, to keep things simpler, you don't need to worry too much about having less than an octet. We're not going to have to worry about that as a separate rule. The only rule that we basically, this is hard enough, so we want to keep things simple. The only rule we really have to worry about is not exceeding the octet rule. Okay, so basically this is starting on a positive charge, so that's not reasonable. But the comments you made were correct. And then did you try to fix that? Let's see. Well, you came up with a pretty creative way to fix that. Oxygen.
I did make one mistake there. Looks like that
Good point. Yeah.
should just be a single bond.
That's right.
Like that.
Okay, good. All right. So the new arrows that you drew are consistent with our rules. Good. How many charges should we change on every step of every mechanism?
2. Yeah, that's true. Yeah, so that should have a positive charge.
Okay. All right. So that's something to keep watching out for. You always need to ask, have I changed 2 charges? Especially in kind of a weird, unusual mechanism like this where you really can't rely on your intuition. Okay. Now, these in real life, these arrows would not work too well, but they are consistent with what we've talked about so far. So those were good. Based on what we've talked about so far, those were reasonable arrows. And the important thing is you saw the original arrows were unreasonable. Okay, so let's rethink the next example. So you had basically gotten that example correct, although you hadn't quite drawn your product correctly. So let's rethink. Do you still agree with your answer for the next problem? Okay. Actually, on this problem, maybe I need to give you a little bit of help with this one. So I noticed you put a negative charge in on the bromine. You might have thought it had a negative charge because it's ionically bonded to the magnesium.
I wasn't sure if the negative should be on the carbon 7 or on the bromine.
Okay, those are good questions. By the way, have you ever seen a reagent like this before? This is what's called a Grignard reagent. Did you see those in the first semester?
I believe so, yeah.
Okay, yeah. So this is what's called a Grignard reagent when you have a carbon connected to a magnesium connected to a halogen. So first of all, you can't assume that the bond with magnesium is ionic, even though it's a metal, because where is magnesium in the periodic table? Which column?
The second.
Yeah, second column. So it's not as willing to lose electrons as the elements from the first column. If we have a bond with sodium or potassium, that's pretty much always ionic. A bond with sodium or potassium, and usually lithium, is always ionic. But other metals, we can't assume that it's ionic. It actually turns out that the magnesium-bromine bond is covalent, not ionic.
Okay.
If the bromine was bonded to sodium or potassium, then we could assume it's ionic. But magnesium is a little bit more borderline because it's from the second column, not the first. So that wasn't a bad guess. I can see how you could come up with that. So that's something we hadn't quite specified before. But magnesium and the bromine there, that's not an ionic bond. So let's erase the positive and negative charges that you put in there. How about the magnesium and the carbon? That one's even trickier. That one is even trickier. That is so borderline that you can draw it either way. You can draw it as either ionic or covalent. That's something that we'll get into more detail when we talk more about Grignards. The magnesium-carbon bond could be drawn as either ionic or covalent.
Okay.
However, notice that we've already drawn a dash between 7 and the magnesium, so we're committed to the covalent picture here.
Okay.
When those dashes always indicate covalent bonds. Covalent bonds, ionic bonds, are never drawn with a line. So if we've already drawn in the line, we're committed to the covalent picture. So we're not going to put any charges there either. So that's a little bit tricky. So we have to. So basically, in this case, we're not going to draw in any formal charges. But that was a little tricky. We hadn't quite spelled that out before. Okay, so in fact, in this case, there are no formal charges in the original picture. There are no formal charges here in the original picture, although we hadn't quite explained that very well before. So you'll probably have to go back and rethink. So now, in light of the fact that there are no formal charges, were the original arrows reasonable?
Not quite. It looks like even were that to attack the carbonyl, that would still require an arrow, that pi bond, to break, because carbon 2's octet was already full. So then oxygen would end up with a negative charge.
Good. That was what I was trying to test with that question. Yeah. What I was trying to test with that question is that it was breaking the octet rule. Okay. So perhaps we should erase where you have there, the arrow should begin on the negative and the positive. That turned out not to be relevant, and we won't need to draw the new products. I think you're good at that point. Okay, so this was unreasonable because it was breaking the octet rule. Let me go back to my screen. Okay. So let's talk a little bit more about these Grignard reagents. These, I think these are usually introduced in the first semester, and they continue to be really important in the second semester as well. So a Grignard reagent looks like this. The general way to write it would be like this. Do you know what does R stand for in OChem usually?
A carbon chain?
Yeah, a carbon chain. So this is any carbon chain. Remember, those are also called alkyl groups. And what does X usually stand for in OChem?
Halogen.
Yeah, usually not fluorine, but chlorine, bromine, or iodine. So it stands for chlorine. So that's the general formula. Okay, so one thing we've seen here then is the bond between the magnesium and the halogen is not ionic. Or, anyway, actually, that might be mistaken. You know, actually, in real life, it might actually be ionic, but there's no point drawing it that way because the halogen is not going to be the reactive atom here. So actually, now that I think about it, there probably is a good deal of ionic character to this bond. In reality, this probably is a somewhat ionic bond, but it's never drawn that way in OChem, and it's not useful to draw it as ionic because it's never the halogen that's reactive in a Grignard. So we're not going to draw this as an ionic bond in any case. So maybe we'll just have to memorize that. We won't draw this as ionic. How about the bond with the carbon here? Well, that's tricky. That could be drawn as ionic because it's kind of borderline. So there's two correct ways to draw a Grignard reagent. There's two correct ways to draw a Grignard reagent. We could draw it like this, or we could draw it like this. Those are both correct. Now, the problem I had given you was already drawn this way. So in this case, there would definitely be no reason to put in the formal charges there. This would be incorrect because you can't. So notice in this picture, are we treating the bond between 3? In this picture, are we treating the bond between 3 and the magnesium as ionic or covalent?
Covalent.
How can you tell? Well, these lines always mean covalent. Lines like this always mean covalent bonds. And in this picture, are we treating it as ionic or covalent?
Ionic.
So it turns out that in this case, you can do it either way. But you can't do both at the same time. You can't treat it as both ionic and covalent. So this would be incorrect. You're not allowed, you have to choose between the covalent and the ionic pictures. You can't combine them. And I'll show you something else that's really incorrect, but that I see students do a lot. So this is supposed to be the same molecule as before. Can you see how this is incorrect?
Yeah, definitely.
What went wrong here?
Both charges are on the magnesium.
Yeah. Now, the student didn't mean that. The student thought they were putting the charge here, but this is not an extra carbon. Actually, what's happening here is the student is accidentally inventing a new carbon. They're imagining that there's a new carbon here at the end, but you can tell that's not right because we already numbered there's only 3 carbons. Okay. All right. So anyway, these are 2 common mistakes. 2 common mistakes. These are the correct ways to draw it. Okay. We hadn't really talked about that before, but now is a good time to talk about this. Grignard reagents are really quite important in both semesters of OChem, and that they'll probably be pretty important on your DAT as well. So now's a good time to clear that up. By the way, this thing that I said here, I said this could be drawn as either ionic or covalent. I'm not saying that's true for all molecules. It's just true for Grignards. Normally, there's only one correct picture. Normally, it's correct to draw it as covalent, or it's correct to draw it as ionic, but not both. But for some reason, it's okay to draw Grignards either way. I think that's because it's kind of borderline between those two. So, for example, are these ionically or covalently bonded?
Those are ionically bonded.
So you would never draw it like this.
Right.
Yeah, you would. Here, we're only going to draw the ionic bonding. But it turns out that Grignards are borderline. It's acceptable to draw them as either ionic or covalent, as long as you choose one of those pictures. I'll show you another type of reagent that's also similar to this.
Okay.
Another reagent that's similar. Very similar, almost identical, actually. A very similar reagent are alkyl lithiums. Their formula is this. What does the R stand for?
Alkyl group.
Right, which is a carbon chain. Those are actually almost identical to Grignards. So here would be a correct way to draw an alkyl lithium. Notice that alkyl lithiums don't have halogens. Alkyl lithiums don't have halogens. So this would be correct. It would also be correct again to draw it as ionic. So this slightly contradicts what we said earlier. Earlier I told you that since lithium is in the first column, it always forms ionic bonds, like sodium and potassium. Earlier I told you that since lithium is in the first column, like sodium and potassium, it always forms ionic bonds, like sodium and potassium. This slightly contradicts that, because in this case it would be acceptable to draw this as covalent as well. It would be acceptable to draw this as covalent because it's kind of borderline, but it doesn't contradict it too badly because the ionic picture is also acceptable. And again, it would be incorrect to try to combine the two pictures. You have to choose either ionic or covalent. And it would be super incorrect to have this negative charge hanging off here at the end of the bond, because that kind of invents a new carbon that doesn't actually exist there. Okay. All right, so these are pretty important reagents, so we may as well be learning these details about this. This is something I hadn't quite specified before. We've seen that it's important to be able to draw formal charges. For these reagents, you don't have to draw the formal charges, though, if they're not given. You could just stick with the covalent picture. Okay. All right, that would be a good thing to review then. So let's see, going back to your screen. Let's see, where were we? So now we can see that the original picture was incorrect simply because it was breaking the octet rule. Okay. All right, so let's go on and now rethink the next problem. Do you still agree with your previous answer?
Yeah, I do.
Okay, yeah. That was a good answer. The previous errors were unreasonable for two reasons. They were breaking the doublet rule on the hydrogen, and they weren't ending on the positive charge. And then you fix that quite easily. Your new arrows do not break the doublet rule because the hydrogen is now both gaining and losing a bond, and now the arrows end on a positive charge as well. So it looks like you got that correct originally. And you also drew the product from that correctly. Okay, so that one you had already gotten correct. Good. Let's take a look at the next example. So do you still agree with your previous answer here?
Yeah.
Yeah. Again, this was breaking the doublet rule. So you tried to fix that. Okay, great. So the arrows that you drew are not the actual arrows that would actually work in real life, but they were consistent with the rules we've talked about so far. So based on what you and I have talked about so far, you came up with some reasonable arrows. They're consistent with the rules we talked about so far. Later on, we'll see more rules that would help us to get better arrows there. But anyway, so you did that problem correctly. That was good. All right, so do you agree now with your answer for the next problem?
Yeah, I do.
Yeah, those are reasonable. They don't break the octet rule. They start on the negative charge. Good. Do you agree with the next answer?
Yeah.
Now, these arrows don't start or end on negative and positive charges, but that's okay because there were no negative and positive charges. And this can't be breaking the octet rule because it's cyclic. Cyclic arrows can't break the octet rule because everyone who's gaining a bond is also losing a bond. So those were correct. They were already reasonable. Good. Okay. All right. Let's keep going. Let's see. So let's decide, do we still agree with our previous answer here?
Yeah, it does violate the doublet on hydrogen. It looks like
Good.
I drew in a positive negative in the way I shouldn't.
Okay, yeah, we hadn't really talked about that before. What you drew seemed very reasonable because we said that lithium forms ionic bonds. Actually, what you drew would have been okay if you had just erased the bond between the 7 and the lithium, right?
Sure.
Because remember, this could be ionic, you just have to choose one of them. But since it was drawn originally covalent here, we may as well stick with that picture. Okay, so in any case, you saw that the original arrows here were unreasonable. And I think you also drew the products correctly. Good. Okay, so that was violating the doublet rule. Good. Next set of arrows. Reasonable. Okay, so do you agree with your answer for the next problem?
Yeah.
Yeah, that those are reasonable arrows. Good. And do you agree with your answer for the next problem?
Yeah, it would be violating the octet rule.
Good. And you came up, and you actually came up with a very good set of arrows to fix that. That was good. You probably haven't seen that reaction before. This is a real reaction from the second semester, so you actually came up with quite good arrows there. By the way, one reason those arrows are good is because they ended up putting the negative charge on an oxygen. Oxygen is fairly electronegative, so if you have to put a negative charge anywhere, maybe that's not a terrible place to put them. Okay. Good. So the important thing that I was testing there was testing to make sure that you were checking that we don't break the octet rule. So it's good that you had checked that. Okay, all right. So there was certainly a bunch of issues came up here. So that's the purpose of the homework assignments. There were a few things we can see here that I hadn't really explained clearly enough in the last session. So by going through these problems, we were able to see where the unclear aspects are. And hopefully now things are clearer. So going back to my screen, here's what we tried to clarify. First of all, I tried to clarify what we've talked about so far. So far, we've talked about really 2 rules. And we want to try to boil things down to as simple and as few rules as possible, because you're going to have to apply these on every single problem for the rest of your OChem life. So they have to be relatively simple so that you can keep applying them. So here's our 2 simple rules. Don't break the octet rule, and put the negative at the beginning and the positive at the end. So some things that we clarified here is it's easy to tell whether something started with a complete octet, because besides carbon and hydrogen with positive charges, almost everything else starts with a complete octet, even if it's charged. And also one thing that we should that's very helpful that I didn't quite emphasize last time is don't put charges in the middle. If you see a charge in the middle of the chain of arrows, that's almost always incorrect, and we can just stop thinking and try to fix that. Okay. Let's see. So, and then also we saw more clearly how to think about these Grignard and alkyl lithiums. We saw that they can be interpreted as either covalent or ionic. But for our purposes, it's not helpful to think of this bond as ionic, or at least it's not helpful to draw it in as ionic, because it turns out that the halogen, basically maybe we can just memorize, the halogen never reacts in a Grignard. The halogen in a Grignard is never reactive. The halogen in a Grignard is never reactive. Maybe we should just memorize that. Okay, because it's not really obvious. And going back to your screen, so let's scroll back up to the instructions here for that problem. All right, I think we had a bunch of issues here. So part of your homework for today is just redo everything from question 3. Do it on a blank piece with a blank set of questions without your answers. So just print out that old problem 3. 1 and 2 you don't have to do again because you did a good job on those. 1 and 2 you did fine on, but you should print out 3 again and just redo that whole set of problems. And again, we can look at them again next time. One thing you can do to save time is remember it's not necessary for you to keep drawing the product from every single, unless you feel like it. Obviously, if you feel like it, that's okay. But I think you've made good progress on drawing the products based on the arrows. So if you want, you can save time and just decide whether the arrows are reasonable or unreasonable. And if they're unreasonable, again, you can try drawing in better arrows. But the most important thing was, and this time, try thinking more specifically about the 2 rules we've specifically talked about so far. Don't break the octet rule, and put the negative at the beginning and the positive at the end. Okay, so that was some important progress. I think we learned a bunch by looking at those. Let me see. So one thing I should mention, it's good that you took the time to work through all of those problems. That was quite a few problems. It's good that you took the time to go through that. One thing that you might have benefited from, though, there was reviewing your tutoring notes more carefully before doing the problems. For example, I think that as you were doing those problems, you didn't have fresh in your mind some of the things we talked about last time, like don't put a charge in the middle of the arrows, or how to tell whether something has a complete octet. Now, that might partly be because I didn't quite make things clear enough last time, so it might partly be on me that I didn't quite specify the rules clearly enough last time. But in any case, something you should think about is before doing the homework problems, make sure that you reviewed your tutoring notes, because remember, the purpose of the homework problems is to practice what we went over in the tutoring. The purpose of the homework is to practice what we went over in the tutoring, so it's good to refresh your memory of your tutoring notes first and then try to apply that to the homework problems. And then when we review those together, if we see there's any issues, that'll be a good way for me to diagnose if there's something I didn't explain clearly enough previously. Like I think here there was a few things I needed to clarify. Okay, so one moment. Let me see. Okay, so let's start by doing a little bit more practice with what we were just talking about. So this is a similar problem to what we were just talking about. Is this arrow reasonable?
No, the phosphorus already has a complete octet, and so that would be violating the octet rule.
That's right. These are unreasonable because it violates the octet rule. How do you know the phosphorus has a complete octet? Well, just because it's not C plus or H plus. So we know it has a complete octet. Okay, good. That was an issue we had before. Very good. Are these arrows reasonable?
No, because there's a formal charge, a negative charge on the oxygen next to the sodium, and that's where the chain of arrows should begin.
Good. So the first thing we'd have to do here is draw in those formal charges. And when we've done that, we can see that this is not reasonable. Okay, good. That was another issue that came up before. Good. So these are unreasonable because we should be using the negative charge in that reaction. Good. Are these arrows reasonable?
No, the positive charge should not be in the middle of the chain of arrows.
Excellent. There's many things you could say about that, but this is the simplest. The simplest is just to say, don't put the charge in the middle. Good. The simplest way to reject this is we know we shouldn't put charges in the middle of the arrows. Good. Are these arrows reasonable?
Yeah.
Yeah. Okay, good. There's nothing wrong with them. I just wanted to go over it. Before you were thinking maybe the chlorine should do something because it has a negative charge. But remember, we've learned that in a Grignard, the halogen is never reactive. It's not helpful to think of this as ionic. The halogen here is not going to be reactive. And we don't need to, we could draw informal charges here, but we don't have to. We can just leave this the way it is. So this is reasonable. Okay, good. Okay, so it looks like we can still use some practice on those ideas, but I think right now the basic rules that we've talked about there are clear. You could use some more practice to reinforce those, but I think those ideas are clear. So I'll let you practice that some more with the homework problems, and I'll move on to our next topic. So let's see. What is the most important factor in organic chemistry?
The charges.
So we're going to continue to use that to try to explain things. Remember, what are we working on? We're trying to come up with rules that will allow us to draw our own reasonable electron-pushing arrows. We're trying to come up with rules that will allow us to draw reasonable electron-pushing arrows. Okay. We've gone over 2 rules so far. We're trying to keep things as simple as possible. Unfortunately, we can't make them too simple. The OChem is complicated, but we don't want to overcomplicate it. So here's 2 rules that we've talked about so far. Now, the next topic that's helpful is to talk about the roles that atoms can play in a reaction. One of the most important tools for drawing your arrows is figuring out what roles the atoms are going to play. So here's what I mean by roles. We're going to start by talking about 3 roles: nucleophile, electrophile, and leaving group. Do you remember having seen these terms before?
I do, yeah.
Yeah, these are actually some of the most important terms in the course. So these are what I call roles. So when I'm talking about roles, this is what I mean: nucleophile, electrophile, or leaving group. All right? So to review, what are 3 roles that atoms can play in organic chemistry?
Nucleophile, electrophile, and leaving group.
Good. Those are very crucial to the course. They're kind of like the pieces in chess. If someone asked a chess player, what are the pieces in chess, they would have absolutely no trouble rattling off the pieces. You know, rook, bishop, knight, queen, king, pawn. No trouble rattling off what the names of the pieces are. So we don't have to, it's important that we should have no trouble remembering what the names of the roles, the pieces are in OChem: nucleophile, electrophile, leaving group. There's actually 2 more roles that we'll talk about later. So right now we'll talk about these 3 roles, and later we'll add 2 more. All right. Well, do you remember this term? How would you define this term? What is a nucleophile?
Something drawn to a positive charge, I guess.
That's a good start. That's a good start. Yes. That's a good start. That's on the right track. Now, let's try to make that into a definition that will be more useful to us. The key thing to focus on for all of these roles is whether they're electron donors or electron receivers. That's the key. Organic chemistry is about moving electrons around. So we have to decide, is this an electron donor or an electron receiver? What do you think? What do nucleophiles do in a reaction? Do nucleophiles donate electrons or receive electrons?
Donate electrons.
So a nucleophile donates electrons. Okay. Now we can add a second, this is the key, but we can add a second part. It donates electrons to join an electrophile. All right, so we need to really memorize this definition. So what did we just say is the definition of a nucleophile?
It donates electrons to join an electrophile.
Okay, good. Now obviously that's fresh in our mind right now, but we need to keep reviewing that so that's always fresh in our mind. Again, it's like the pieces in chess. Anytime you ask a chess player, how does a bishop move? They can tell you right off the bat, it moves diagonally. How does a rook move? It moves in columns and rows. They don't have to think about it. They just know it automatically. So we need to know automatically in our bones the definition of a nucleophile, because this is such a crucial idea in organic chemistry, crucial on every step of every reaction almost. All right, so that's our definition of a nucleophile. And now maybe it would help to see an example. Who is playing the role of nucleophile in this reaction?
The iodine.
And you can see, is it really donating electrons?
Yeah.
Because it's at the tail.
Yeah.
The thing at the tail is donating its electrons. And is it really joining an electrophile, joining something else? Yeah, who is it joining?
Carbon 3.
There you go. That's right. Okay, so now our next role, what's another role in organic chemistry besides nucleophile?
Electrophile.
So let's try to come up with a definition. What would be a good definition for the word electrophile?
It looks like it receives electrons to join nucleophiles.
Excellent, great. So one thing you did that was good there is you tried to make a definition that was kind of parallel to this definition, and what you came up with was exactly right. An electrophile will receive electrons to join a nucleophile. So these are crucial ideas, just like it's crucial to know how the pieces move in chess. All right, good. Now, there's many other possible definitions, but these are the definitions that I think are most useful. So we basically want to memorize this word for word. I guess I'll be kind of bossy here and say we should memorize these definitions word for word because they're so important and so useful to us. Okay, so how would you define a nucleophile?
A nucleophile donates electrons to join an electrophile.
Good. And how would you define an electrophile?
An electrophile receives electrons to join a nucleophile.
Great, great. And it might seem picky, but I think it's best to really memorize those word for word, just like you were just doing, because these concepts are so crucial for the course. Okay, very good. How can we remember these definitions? Obviously, they're fresh in our mind right now. Well, I think this one's particularly easy to remember because do you know what phile means? I think that's from Latin or Greek. Do you know what phile means?
It means drawn to, attracted to, or likes.
Yeah, like it means it likes something. So why is this a logical name for this role? How does this name match this definition?
It says it likes electrons.
So would that mean that it wants to donate them or receive them?
Receive.
Yeah. So if you like cupcakes, does that mean that you want to take cupcakes or give cupcakes?
Take them.
That's right, yes. So if you're a cupcake phile, that doesn't mean that you go around giving other people cupcakes. It means that you try to steal the cupcakes from other people. So an electrophile is not going to give other people its electrons. It's going to try to steal the electrons from other things. So I think this definition should be super easy to remember because it looks like you already know that phile means lover or liker. So it's very easy to remember that electrophiles receive electrons. This is the key part of the definition, that it's receiving electrons. So that should be easy. Now this name, I think, is a little bit more opaque, a little bit harder to remember. Here's my suggestion, though. If you have trouble remembering what a nucleophile is, just remember what an electrophile is, and remember a nucleophile is the reverse. I think that might be the easiest thing. If you ever forget what a nucleophile does the nucleophile donate or receive electrons? Well, just remember what an electrophile does. Obviously, electrophiles receive electrons. Well, a nucleophile must be the opposite. We can explain why this makes sense a little bit more, though, because nucleo here refers to a nucleus. Well, do you remember from your chemistry course, what's the charge on a nucleus?
Positive. So
this really means a positive lover, a positive liker. Well, do you see how how is that consistent with this definition? Who would you donate electrons to? Do you donate electrons to something that's positive or to something that's negative?
You donate electrons to something that's positive.
That's right. Why is that? Well, do you remember what's the charge on an electron?
Negative.
Yes. And do like charges, so does a negative want to find another negative or a positive?
Positive.
Yeah. So if you're going to donate electrons, you can't donate electrons to somebody who's negative because it would just repulse the electron. If you want to donate your electrons, you have to donate your electrons to somebody that's positive. So the name, that's where the name comes from. So you could also use that to remember what a nucleophile is. You could say nucleophile means nucleus liker, but the nucleus is positive. Remember, the most important factor is the charges. So this really means positive liker. Well, if you like things that are positive, that's not because you want to take electrons from them, it's because you want to give them electrons. If something has a positive charge, does that mean it wants to receive electrons or donate electrons?
Receive.
And who could donate electrons to it? The nucleophile. Okay, so that name hopefully now makes sense. Unfortunately, the name, it does take a couple seconds to figure out why the name makes sense. So if you forget what a nucleophile is, you could try to figure it out by remembering that it's a positive liker. But if that works for you, that's fine. But I think maybe the easiest thing, again, is just if you forget what a nucleophile is, you can remember what an electrophile is, because that name makes good sense. Electrophiles receive electrons, and then you know a nucleophile is the opposite. Okay, anyway, one way or the other, we have to have memorized these two names. They're very crucial for us. Notice, even though so in this problem, do you see any electrophiles? Who's acting as the electrophile?
The carbon-3.
Because it really is receiving electrons from this arrow, and it's joining the nucleophile. Good. So this is the electrophile. Notice that even though nucleophiles like reacting with things with positive charges, they don't always have to react with something with a positive charge. This does not have a positive formal charge, but it still is possible for it to act like a electrophile. We can talk about that more later. Okay, so what is our definition of a nucleophile?
A nucleophile donates electrons to join an electrophile.
Good. And what's our definition of an electrophile?
An electrophile receives electrons to join a nucleophile.
Okay, good. Oftentimes, we might just shorten it to this. Nucleophiles donate electrons and electrophiles receive electrons. But sometimes it's helpful to remember this part of the definition as well. Well, we've talked about there's one more role we've mentioned so far. What's the third role besides nucleophile and electrophile?
Withdrawing group.
What was the name of that again?
Was it withdrawing group?
That would be a logical name, but the actual name that's used is leaving group.
Leaving group, yeah, that's right.
Who's the leaving group here?
The chlorine.
So, notice, do you see the big difference between, well, first of all, let's focus on the electron definition. You can tell from this example, do leaving groups donate electrons or receive electrons?
Receive.
But that's something you might not have really thought about too much when you took the first semester. Oftentimes students don't think about that. A lot of students don't realize leaving groups receive electrons. So that's crucial. Leaving groups receive electrons or take electrons.
Yeah.
That's not really obvious from the name, is it? So that really has to be memorized. Or you could just think of an example like this to see that the arrow is pointing towards the leaving group, which shows that it's receiving electrons. Because the arrow shows the movement of what?
Electrons.
Yeah. But wait, we said electrophiles receive electrons. How can they both receive electrons? If they're both doing the same thing, why do we need two different names? If they're both doing the same thing, why do we need two different names? Well, that's where the second part of the definition comes in. Notice that notice electrophiles and nucleophiles join something else. Yeah. But leaving groups leave something else. So that's why we need the second part of the definition. Like I said, the first part of the definition is usually most important, but we need the second part of the definition or we couldn't see any difference between electrophiles and leaving groups. Electrophiles join something, but leaving groups leave something. An electrophile receives electrons to join something, but a leaving group receives electrons to leave something. Now, in this case, it's really obvious. It's very easy to remember that leaving groups leave something from the name, right? The name makes it very clear that a leaving group will be leaving something. this name does not make it clear whether the leaving group is receiving or donating electrons. That just has to be memorized. Or hopefully this might be a particular familiar reaction to you. This is one of the first reactions you learn in the first semester, an SN2. So if you just imagine this SN2 reaction, you can remind yourself that the leaving group is at the head of the arrow and it receives electrons. But that's something that we need to have memorized. Okay, so here's our three pieces that we've talked about so far. Good. So what is the name of one of the roles in organic chemistry?
A nucleophile.
How would you define a nucleophile?
A nucleophile donates electrons to join an electrophile.
All right, what's the name of another role in organic chemistry?
Electrophile.
And what would be its definition?
It receives electrons to join a nucleophile.
Great. And what's another role?
Leaving group.
And what's its definition?
It will receive electrons and leave something.
Rather than join.
Yeah.
What's the name of the thing that reacts with the nucleophile?
The electrophile?
Yes. And what's the name of the thing that reacts with an electrophile?
A nucleophile.
Good. So nucleophiles react with electrophiles, electrophiles react with nucleophiles. So for example, do nucleophiles react with other nucleophiles? No. Remember that our goal here is that we're going to want to be identifying who's going to be the nucleophile and the electrophile. We want to identify who's going to react with who so we can draw our own arrows. Well, one principle is you don't react a nucleophile with a nucleophile. You react a nucleophile with an electrophile. Would it be reasonable for an electrophile to react with another electrophile?
Sorry, could you repeat that question?
Would it be reasonable for an electrophile to react with another electrophile?
No.
No, so we wouldn't want to do that, and we're coming for their own arrows. That might seem obvious, but I see students do that all the time. We want to react so how do you draw your arrows? You try to figure out a nucleophile and then try to figure out an electrophile and react them with each other. By the way, notice that there's no real name for what the leaving group leaves. I'm just going to be unsatisfactory here and call it something. It'll leave something. There's no official name that I'm aware of for the thing that the leaving group is leaving. That's always going to be appropriate. Oftentimes they leave an electrophile, but that's not always the case. Okay, very good. So let's see. So our next job then is we need to start figuring out how we can identify who's going to play what role in the reaction. So let's see. So to review, nucleophile. What's the definition of a nucleophile?
A nucleophile will donate electrons to join an electrophile.
So now, how can we identify the nucleophile? Well, what's the most important factor in organic chemistry?
Charges?
Yeah, so that's what we want to focus on. How can we use charges to identify the nucleophile? And we're going to start by focusing on formal charges, which are the most important type of charge. Well, what type of formal charge would make something a good nucleophile?
Negative charge.
Okay, so what we're going to go over here, as we've been doing before, we're going to have a rule. And then, unfortunately, later we'll have to go over an exception. But we'll start with the rule. So if an atom has a negative charge, what role is it likely to play?
A nucleophile role.
So this is the general rule. Things with negative formal charges tend to play the role of a nucleophile. All right, good. So would this go at the head or the tail of an electron-pushing arrow?
At the tail.
Now, where exactly should I draw the tail? Well, here I would draw the tail on the negative charge. So, for example, this is wrong. You're not allowed to put the tail directly on an atom. You're not allowed to put a tail directly on an atom. We haven't talked about this before, but you're not allowed to put a tail directly on an atom. You can put the head on an atom, but you can't put the tail. Instead, the tail has to go somewhere that's not directly on the atom. For example, you can put the tail on a negative charge. What does this really represent? Is this atom donating or receiving electrons?
Donating.
What electrons is it donating? Where are the electrons coming from that this atom is donating?
The valence shell.
Good. To be more specific, are they coming? They're coming from a lone pair, is what I was going for. It's kind of a weird question, but they're coming from a lone pair. There's really only two places you can get electrons from. The only two places you can get electrons from are bonds and lone pairs. So this is coming from a lone pair. Nucleophiles usually donate electrons from a lone pair. So this is an example of something that's donating electrons from a lone pair. So that's our rule. Okay, let's see. So let's try to predict what's going to happen here. So can you identify what's the atom we should focus on first here?
The iodine.
Why the iodine? The iodine looks just the same as all the other atoms. Why should we focus especially on the iodine?
It has a formal negative charge.
That's right. Yeah. All right, so what role do we expect the iodine to play?
Nucleophile.
So does it go at the head or the tail of an arrow?
Tail.
I'm going to stop right there. Now, you might already know where I'm supposed to put the head of this arrow. You might have seen this reaction before. You might know where the head should go, but we haven't talked about any rules yet for figuring out where the head will go, so we'll do this systematically. Based on what we've talked about so far, this is as far as we can get. It would be nice if we could put the head pointing, remember that we'd like to put a positive charge at the end of the arrows, but there is nobody here with a positive formal charge except for the spectator ion. So you might already know what the rest of this reaction is, but we can't justify it based on the rules we've talked about so far, so I'll just draw this. One reason I'm doing this is a very important skill in organic chemistry. One big problem I see that students have is they're not willing to write down any arrows unless they know all the arrows. A mistake that students make is they're not willing to write anything down unless they know the complete answer. But that's a mistake because one of the best ways to think is to think on paper. If you only know part of the answer, you should write down the part of the answer that you know, and then maybe that will help you to figure out the rest of it. So my point is, if you only know where the tail of the arrow goes, and you don't know where the head of the arrow goes, then just write down where the tail goes, and say that you don't know where the head goes yet. That's a useful skill in organic chemistry. You should be willing to write down just where the tail goes or just where the head goes, if you only know that part, and then you can try to figure out the rest. Okay, good. Let's see. Let's see. Actually, I can see here there's something I actually wanted to talk about that I forgot to talk about. So this is a little disorganized, but let's try this. Before we started drawing the arrows, I realized I wanted to talk about something else. Let's start by practicing identifying the roles. So you can identify what roles are atoms playing here. Who's playing what roles?
Looks like chlorine is the nucleophile, carbon-2 is the electrophile, and bromine is the leaving group.
Excellent. What roles can you identify here?
It looks like nitrogen is the nucleophile. That secondary carbon, I guess that's what it would be. It would be the number 2 carbon would be the electrophile, and the oxygen attached to the sulfur, that whole molecule there is a leaving group.
So which atom is the leaving group?
The oxygen.
Good. So these terms are a little ambiguous. They can refer to a part of a molecule or just to one atom. We could say that this oxygen is the leaving group, or we could say that this whole fragment is the leaving group. Those are both correct. But it's more useful right now to focus on the atom. So the atom here that's the leaving group atom is the oxygen. Okay, good. What roles can you identify here?
Looks just like a leaving group.
Who's the leaving group?
Bromine.
Okay, good. That's right. This is a kind of a different pattern than we saw before. Sometimes a leaving group can just leave without being forced off by a nucleophile. Sometimes a leaving group just leaves without being forced off. You can kind of see why this makes sense, because you know that the product would look like this. Is this an acceptable carbocation?
Yeah, it's a secondary.
Yeah, so this is acceptable. The leaving group can just leave without being pushed off because it forms an acceptable carbocation. So sometimes leaving groups just leave. So this is a leaving group. This reaction has a leaving group without any nucleophile or electrophile. That's what you said, so that's good. What roles can we identify here?
A leaving group.
Which?
The oxygen.
Yeah, the oxygen is the leaving group. And that's pretty much it. Just a leaving group. Good. What roles can we identify here?
The oxygen is the nucleophile. The carbocation is the electrophile. And there is not a leaving group.
Yeah, so here's another pattern that we hadn't seen before. Sometimes you don't need a leaving group. By the way, why don't we need a leaving group here? Well, is this going to break the octet rule?
No, because there's a deficiency of electrons.
That's why we don't need a leaving group. Yes. Notice, did we need a leaving group in this reaction?
Yeah, we did.
Because this started with a complete octet. So we're seeing there's a few different patterns here. It's possible sometimes to have a nucleophile attack an electrophile without a leaving group if you start with an incomplete octet. Okay, good. What roles can we identify here?
It looks like the oxygen with a negative charge is the nucleophile, while carbon number 2 is the electrophile. And I'm not sure if that oxygen is called a leaving group. It broke a bond like a leaving group would, but it didn't completely leave.
The molecule. Okay, that's a good analysis. Yeah, we should consider this a leaving group because it is completely leaving carbon too. It's true that it's not leaving the molecule, but it is leaving carbon too completely, so it is considered a leaving group. Yes. Okay, so that was a good thing to think about. This is a little different than before, but this is still considered a leaving group. Good. And notice, what was the definition of a leaving group?
It receives electrons to leave something.
Certainly this is receiving electrons, so it certainly matches that part of the definition. And it is leaving carbon too. Okay? What roles can you identify here?
Bromine on the right with a negative charge would be the nucleophile. Carbon number 2 would be the electrophile. And bromine with positive charge would be the leaving group.
This is similar to the previous example. The bromine is leaving carbon too, even though it's not leaving the complete molecule. So it is a leaving group. Good. Let's identify some roles here.
Okay. Carbon number 1 is the nucleophile. Carbon number 3
Whoop, oh, I'm sorry. Excuse me. I drew incorrect arrows. Sorry about that.
Okay.
1 second.
Okay.
So let's try again. What are the roles now?
Carbon number 1 is the nucleophile. Carbon number 4 is the electrophile. And oxygen above carbon 4 would be the leaving group.
This one's tricky again. This one, it's probably best not to use the term leaving group because it's actually not leaving carbon 4. Okay. Right? It's still going to be connected with the sigma bond, right? This is a little bit a matter of the definition. You could go either way, but I don't think it's usually considered a leaving group. It's in many ways it's similar to a leaving group. In many ways it's similar. You might think of it as a kind of a pseudo leaving group or similar to a leaving group, but it's probably better not to consider it a real leaving group because it's not actually leaving carbon 4. Okay, so you might want to compare these examples. This really is a leaving group because even though it's not leaving the molecule, it really is leaving carbon 2. But this is probably, we would not use the term leaving group because it's actually it's not leaving carbon 4. It'll still have a sigma bond, although it does have some similarities to a leaving group. Okay, good. Let's identify some roles that are being played here.
Okay. Looks like that hydrogen is the nucleophile that's attached to the aluminum. And carbon number 2 is the electrophile. And oxygen, I guess, is our pseudo-leaving group.
Okay, right. That's right. It's kind of like a leaving group, but not really. It's not, we wouldn't use the term leaving group for it. So that's what you said. Now, this is a kind of one of these kind of ambiguous arrows we've seen where the tail is between two atoms. Why did you say the hydrogen would be the nucleophile instead of using the aluminum as the nucleophile?
Well, said the hydrogen because that would neutralize the charge on the aluminum.
Excellent. So that was right. That was a correct analysis. Notice I don't think that's what a naive student would say. A naive student might say, oh, the negative charge is on the aluminum, so the aluminum is the nucleophile. But that turns out not to really make sense if you think about it more carefully. If the aluminum was the nucleophile, it couldn't actually get rid of its negative charge in this particular type of reaction. To get rid of the negative charge, we need the hydrogen to be the nucleophile rather than the aluminum. So you figured that out correctly. That's good. By the way, where is the hydrogen getting the electrons from that it's donating?
From its covalent bond with aluminum.
Right. Remember we said earlier there's only two places to get electrons, lone pairs or bonds. Most nucleophiles get electrons from lone pairs. Most electrons take electrons from their lone pairs. This is an unusual nucleophile that's taking the electrons from a bond. That's right. Where did this nucleophile get its electrons from?
This up there got it from its lone pair.
Right. We didn't draw in the lone pair, but we know that's what the negative charge is standing for here.
Yeah.
Where did this nucleophile get its electrons from?
A lone pair.
Good. How about this nucleophile?
Also a lone pair.
Good. How about this nucleophile?
A lone pair.
Good. Notice here we didn't use a negative charge. We actually drew in the lone pair. Remember, you're not allowed to do this. You're not allowed to have the tail directly on the atom. Instead, the tail has to be on a negative charge, or you have to draw in a lone pair, or put the tail on a bond. Those are the rules. Okay, good. So that's good that you saw that it was the hydrogen here that was the nucleophile, not the aluminum. All right, let's identify the roles here.
Okay, carbon number 3 is the nucleophile. Carbon number 5 is the electrophile. And the nitrogen is the pseudo-leaving group. It doesn't
it's not a real leaving group, but it's kind of similar to a leaving group in some ways. Okay, good. Excellent. How did you know that carbon 3 would be the nucleophile here and not the magnesium, since the tail is between the two of them?
It's a Grignard reaction, and the carbon number 3 has claim on the electrons from that covalent bond.
Good. You could just memorize that. Grignards are so important, you could just memorize that. But why does that make sense? Why would we expect the carbon to have claim, so to speak, on the electrons rather than the magnesium?
Well, you would be forming a primary carbocation on carbon number 3. You shouldn't do that.
That's true. That's probably not the best explanation, though, because who would be the nucleophile here?
Still carbon 3.
So we don't want to focus too much because that would on whether it's primary, secondary, or tertiary. What we want to focus on is who's going to have to lose the electrons here? Who wants to lose electrons more, carbon or magnesium?
Magnesium.
And how do you know?
It is in the second column of the periodic table.
So it's to the left of carbon.
Left, yeah.
All right, so that's the best explanation here. The magnesium is going to be losing the electrons, so it can't form the new bond. So carbon 3 is going to be the one that actually moves the electrons into the new bond. Okay, you might just memorize how Grignards work, but it's also good to understand why they work that way. All right. What roles can you identify here?
Iodine is the nucleophile. Carbon number 4 is the electrophile. And sulfur is the leaving group. It leaves the bond with carbon 4.
Good. That's right. That's right. What roles can we identify here?
It looks like oxygen would be an electrophile, but it's not fully donating those electrons. It's still...
Can you repeat that sentence again?
Sure, yeah. It looks like oxygen is acting like a nucleophile, but it's not fully donating the electrons. It's still sharing the electrons with carbon-2. But there is definitely a leaving group, oxygen, on the bottom.
Okay, this one was tricky. Now, the first comment you made wasn't quite on point. You said this is not a nucleophile because it would still be sharing the electrons. But that's actually true for all nucleophiles. After all, this iodide here, if it forms a new bond with carbon-4, it would still be sharing the electrons in that bond. When carbon-3 forms a new bond here with carbon-5, carbon-3 will still be sharing the electrons in that bond. So all nucleophiles continue to share the electrons that they're donating. That's an interesting point, by the way. Notice that, remember, what was the definition of a nucleophile?
Donates electrons to join an electrophile.
But notice, just because they're donating the electrons doesn't mean they completely lose them, does it? Because remember, there's three different levels. There's owning electrons, there's sharing electrons, and then there's completely lacking electrons. So a nucleophile might just be moving from owning to sharing. Or even, actually, sometimes a nucleophile moves from sharing with one atom to sharing with another. So nucleophiles actually never completely lose the electrons. Nucleophiles never completely lose their electrons. They just change to some type of sharing. Okay. The key thing here is this is really not considered a nucleophile. It's a little tricky to explain. It's because this is actually, in a sense, a resonance arrow. So I don't want to get into this too much right now, but anytime any arrow that only involves lone pairs and pi bonds is a resonance arrow.
Okay.
Hopefully we'll talk more about resonance later.
Yeah.
I'm not going to get into that too much right now, but I just wanted to mention, if you remember, resonance is not the same as a reaction. So this is not really, in a sense, a necessary reaction arrow. It's more of a resonance arrow. And so those are not considered, resonance arrows do not indicate nucleophiles or electrophiles specifically. So this is very similar to a nucleophile. All right, this is kind of, I guess different people would have different, some people might call this a nucleophile. But maybe it's better just to say this is just the leaving group. So that's a little bit tricky. Maybe there's not a completely standardized terminology for this, but I think it's best for us to say this is kind of like a nucleophile. This is acting like an electrophile, but because it's a resonance arrow, maybe we won't use those terms. The important thing is this is definitely a leaving group. Okay. This here is definitely a leaving group. Okay. Okay. All right. So, all right. So I was a little bit unorganized there. So I wanted to go and give you some examples of nucleophiles, electrophiles, and leaving groups. And now we can go back to the topic that we kind of left off. So now we're ready for this topic that I already mentioned to you, the rule for identifying nucleophiles. Atoms with negative charges are usually nucleophiles. And where would this atom get the electrons from that it's donating?
A lone pair.
Okay, so we saw this example.
Uh-huh.
Okay, so see if you can identify some roles that atoms could play here using the rules we've talked about so far. So what's the one atom here we should be particularly focusing on?
Carbon-4, because it has a negative charge.
Good. So what role would it play?
The nucleophile. Yeah.
So would it go at a head or a tail?
Tail.
And based on what we've talked about so far, we won't know yet who goes at the head. Now you might know anyway, but I won't write down anything more because we haven't gone over the rules for who would go at the head here. Okay, remember, if you only know half of where the arrow goes, it's good to just draw that half. Okay, good. So let's try to put in some electron pushing arrows here. So can you identify where would be a good place to put the head or the tail of an electron pushing arrow here?
The tail of the electron pushing arrow could go on the negatively charged bromine, and that would be a nucleophile. And the head of the arrow should go on carbon number 2, it's a carbocation, which would be the electrophile.
Is this going to break the octet rule?
No, because carbon with a positive lacks electrons.
Great. So in this case, you can figure out the entire string of arrows. Because there was both, when there's two charges, it shouldn't be too hard to figure out reasonable arrows. When there's two charges, it shouldn't be too difficult. So clearly this is the nucleophile in this case with the negative charge, and you were able to figure out the other arrow as well. Good. Okay, can you figure out what would be a logical place to put the head or the tail of an arrow here? Or what would be a role that someone's going to play?
The oxygen next to potassium has a negative formal charge, so that would be a good place to begin the arrow. And it could act as a nucleophile.
Okay, and I'm just going to stop right there.
Okay.
So you might be able to figure out where the head would go, but we don't have any rules for that here yet, so I'll just stop here and say this will be the nucleophile. And so far, we'll just leave this as a question mark, although you might have a pretty good guess as to where this goes. Okay, very good. So the important thing was to notice this type of charge doesn't have to be drawn for you. This type of charge you're supposed to be able to draw in yourself. Good. All right, so let's try to figure out where we could put in a head or a tail here. What would be a role that one of these atoms would play?
Okay, carbon number 5 would be a good nucleophile, and the tail of the arrow could be there.
Good, and I'll just put a question mark for the time being for the head. Now, this might not seem very exciting, but this is a reaction that I know you've never seen before. This is a second semester reaction that you've never seen before. But even though you've never seen this reaction, you were still able to figure out at least part of what was going to happen using these rules. So this might not seem too exciting, but this is one of the key skills. In OChem, we're not supposed to have to memorize every single detail of every reaction. As we internalize these rules, we'll be able to figure out more and more of what would happen. So we're already able to figure out at least half of what's happening here based on the fact that we're using this negative charge to show this is the nucleophile, even though you haven't ever seen this particular reaction before. It's not super complicated, but it's amazing how often students just ignore the charges. So if we just pay attention to the charges, that gives us a big head start in figuring out what will happen. Good. I'm going to have a little digression again. Something else I thought of. So changing gears a little bit, on this problem I've drawn the arrows for you, and I just want to get a little bit more practice with identifying roles. Can you identify any roles that any of these atoms are playing in the reaction?
And they almost look like resonance arrows if they're just involving lone pairs and pi bonds. I mean, typically the head or the tail of the arrow would be where the nucleophile is. That first oxygen on the left is acting like a nucleophile.
Okay, you are on the right track here. So does this look like a resonance arrow?
Yeah, it does.
Because it's just involving a lone pair and a pi bond. Good. Does this look like a resonance arrow?
Yeah.
Because it's moving a pi bond into a lone pair.
Yeah.
So we're probably not going to assign any roles, particularly based on this arrow or this one, because those could be interpreted as resonance arrows. Is this a resonance arrow?
No, actually, it's not.
It does involve a pi bond, but it's also forming a sigma bond, right? So this is a genuine reaction arrow. So this is the one we can use here to identify some roles. What roles could we identify based on this arrow?
Well, carbon 3 would be acting as a nucleophile. Carbon 2 cannot because it's receiving a new bond with oxygen above it.
That's a good point. This arrow is not ambiguous. It's 3 that will be the nucleophile because carbon 2 is already busy receiving electrons from the oxygen. Good. Any other roles we could identify here?
Carbon 5 would be the electrophile.
Okay. So this was another slightly different pattern. You can see there's quite a few different patterns of how nucleophiles, electrophiles, and leaving groups can react with each other. So that's what I was going for here. So notice the nucleophile does not always have to be at the start of the chain of arrows. The nucleophile does not necessarily have to be at the start of the chain of arrows. It could also be more in the middle of the chain, like we have here. This carbon 3 is donating the electrons from this bond to share them with carbon 5. So this is a new slip pattern. But arrows that could be interpreted as resonance arrows, we generally don't assign roles for those. But that's good that you noticed that, but this was not a resonance. You can't have resonance between two separate molecules, by the way. Any arrow between two separate molecules is always going to involve forming a sigma bond, so that would never be resonance. Okay?
And so will a nucleophile always form a sigma bond?
That's a good question. I think that's true. That's a good point. I think that really the way we use the term nucleophile, a nucleophile is always forming a sigma bond. That's right. Because if it was forming a pi bond, it would generally be more of a resonance type arrow. That's right. And we generally would not, you wouldn't always use you usually wouldn't use the word nucleophile for that. I'm not sure everybody is always 100% consistent with how I'm describing that there. That's a little bit borderline again. But yeah, generally speaking, we're going to use the term nucleophile for forming sigma bonds. That's right. Okay? Okay, so can you identify any roles here?
Yeah, it looks like carbon 5 is acting as a nucleophile, carbon 1 as an electrophile, and bromine as a leaving group.
Good, perfect. That's right. Very good. What roles could we identify here?
Carbon 2 is the nucleophile. Carbon 4 is the electrophile.
Good. This is kind of like a leaving group, but we don't usually use that term for it because this is more of a resonance type arrow. Good. So notice it's not the oxygen that's the nucleophile here. Even though the oxygen has a negative charge. Even though the oxygen has a negative charge, in this particular case, it's actually not acting like the nucleophile. But it's still consistent with our rules because notice it's still at the start of the chain of arrows. The negative is still at the start of the chain of arrows. It's still going to be losing its negative charge, even though it's not really acting like the nucleophile in this case. Okay, good. Okay, I guess we're about out of time, so let's summarize what we've gone over today. Remember, one thing that went a little bit wrong after our last session is, at our last session, I think we hadn't quite done a good enough job of summarizing the key ideas for you to use on the homework problems. So let's try to summarize what are the key ideas we talked about that you should be trying to use on the problems. So first of all, here's the key ideas from our previous session. Here's the two rules for evaluating whether arrows were reasonable. Don't break the octet rule, and put negative at the beginning, positive at the end. Don't put charges in the middle. Remember, we saw it's pretty easy to tell whether something has an incomplete octet, because these are basically the only things that don't have complete octets. That was a review from the previous session. We learned some new stuff about how to interpret Grignard reagents here, and alkyl lithiums. Okay, and then we moved on to this new material of the roles. So this is really crucial. Remember, this is something we're going to be pretty picky about. We want to memorize these definitions word for word because they're so crucial to us. So here's these three crucial definitions. Remember, these are what we can call the roles in organic chemistry. And we've learned how to identify what roles things are playing. And then we started going through how to identify nucleophiles and electrophiles and leaving groups. We just got started on that. But we went over our first rule, which is that an atom with a negative charge, not surprisingly, is generally going to be a nucleophile. There are some exceptions to that we didn't get to talk about yet today. But generally, an atom with a negative charge is usually or oftentimes going to be the nucleophile. Okay. And then we can build on that in the future. You should redo problem 3 from that last homework assignment. It would be good practice just to redo the whole thing. We want to get to the point where those problems are just easy and natural for you because those are just going to be part of harder problems. Basically, what we're trying to move on to now is you're going to start drawing your own electron-pushing arrows, and you're going to have to evaluate whether your arrows are reasonable. And we want you to just have internalized those rules so you're applying them automatically. So you can go back and redo that problem 3 because we did have some issues there. Good, and I might send you a few more problems to look at as well, and then we'll try to continue on next time. So our next job again is now we're really working on some of the heart of organic chemistry, some of the most important issues. How can you identify who will be the nucleophile, electrophile, and leaving group? So when we meet again, we'll continue working on that. How can we identify who will be the nucleophile, electrophile, and leaving group?